Welcome to Module 1, which is the representation of information. Computers run a set of instructions called programs that basically manipulate data. Since the computer is an electronic equipment, there should be a way of storing and representing these programs and data. When we say manipulate data, we actually mean apply certain operations to the data. The most common operations used in computer are the arithmetic and logic operations. But the representation of operands in the computer is different from that used by humans, as such, a computer follows a different method in doing arithmetic. Computers basically use a binary system for representing data, while human beings use a decimal system. For human beings to understand what comes out and to be able to instruct computers in the representation it understands, we also look at how conversion from one base system to another is carried out. At the end of this module, you should be able to differentiate the representations used to represent the different types of data like character, integer, real numbers, etc. Explain how a program is represented in the memory of the computer, carry out computer arithmetic on paper, and convert a number from one base system to another. So those are our objectives for Module 1. All data and programs are ultimately represented by sequences of binary digits or bits in the computer memory. The memory consists of a large number of storage cells. So each cell is capable of storing one binary digit called bit. A bit is a distinction between two possible states like 0 or 1, high or low, off or on, or others. Now, memory locations. These are fixed length bits in the computer memory which has a unique address. And memory addresses is usually used by a program to locate data in the memory. Normally, it uses hexadecimal notation. Computer memory also is where data are kept until they are no longer needed. Now remember that a bit is a one-digit number. A byte is usually groups of 8 bits, and a word is groups of 16 bits or 32 bits or 64 bits. To facilitate extraction of bits within a byte or word, the bits are numbered from right to left starting with bit 0. So for byte addressable memory, since it is a byte, we have 8 bits, starting from 0 to the 7th bit, with 0 on the rightmost as your least significant bit, and 7 as your most significant bit. For word addressable memory, you will have 16 bits. Let's say we have our self-assessment question. The 5382nd bit in memory is found in what address in a byte addressable memory, and B, 16-bit word addressable memory. So to answer this one, we have to take note that byte addressable memory is an 8-bit memory. So practically, you just have to divide this 5382 bit by 8 to found the address, which is at 672 byte address located in bit 2, related to that remainder 6. And word addressable memory is a 16-bit memory, so you just also divide it with 16 to get that location at bit number 10 of word address 336. Important rules to remember with regards to the number of bits and number of values they can represent are: number 1, a set of n bits can take on any of 2 to the n values. Number 2, to represent n values, we need the logarithmic of n to the base 2 bits, where this symbol indicating a rounding up of to the next integral value. So suppose we have 538 values to represent. How many bits will we need to represent these values? With this number of bits, how many values can we accommodate? So to answer this, we need to get the logarithmic value of 538, which is 10. And this means there are 10 bits we can accommodate up to 2 to the n, which is 1024 values. Number systems. Now, computers use a different number system from humans, which may be one reason why computers compute so much faster. There are different number systems that we would encounter, like binary, octal, and hexadecimal. We have to remember that in decimal number system, the base is 10. Binary number system, the base is 2. Octal number system, the base is 8. And hexadecimal number system, the base is 16. This table is just an example of a few numbers and equivalents they have. Please take note of the differences between each number system. For octal, it doesn't have 8. And for hexadecimal, there are letters A to F with equivalent numbers in decimal also. So the possibilities of conversion among bases, this is the possibility. So I think any or all are possible from one number system to another. So just for fun, we have decimal to decimal number system. So we have to take note and remember that decimal number system is to the base 10 here. And the weight will always start from the right at 0, where the base is raised to that weight and multiplied with the number digit on that specific weight. Then after multiplying, you get the product and you add the products to get that number that you needed in a different number system. So from binary to decimal, technique is to multiply each bit by the base of what is given to the n, where n is the weight. And this weight is the position of the bit starting from 0 on the right. So looking at our example, the rightmost bit is 1. So that means this one is multiplied with the base 2 and the weight at 0. Moving on to your left, 1 times 2 to the 1, which is 2. Getting the product, you are going to add these numbers to get the decimal equivalent of this binary number. The same is true with octal to decimal number system. Only the difference is that the base is now 8. Okay, so looking at our example, so 4 is the rightmost. We'll have the weight of 0 for that base 8. Multiply it with 4. You get that product and you add. So this is equivalent of 728 octal number to decimal number system becomes 468. Now for hexadecimal to decimal, the technique is still the same, such that we multiply each of the bit, but the base is now 16. Now remember that hexadecimal numbers have letters, so if you will see letters, you have to get the decimal equivalent of each of that letter, basically, and then multiply it with the base, then you add. From decimal to binary, the technique here is to divide by the base of what is asked. So if it's binary, it is number 2. So remember that the first remainder is bit 0 or the least significant bit. That means it will be written from the rightmost going to your left, the remainder. So in our example, we have 125 to the base 10. Is this in binary? So we divide 125 with 2. Then we get 62 with a remainder of 1, which means this 1 here is our least significant bit, and the next it will be written in the rightmost, and the next remainder will be going to your left. until you reach a quotient of 0. For decimal to octal, we have a technique of dividing it by 8 and still keeping track of our remainder. So if you get a remainder of 8, that means your computation or calculation is wrong. So the same technique from decimal to octal. And the same is true with decimal to hexadecimal, such that your divisor will be 16. Now if you get a remainder of greater than 9, so you have 10 up to 15, you have to convert that into letters in hexadecimal. You do not write the remainder in 2 digits without converting it to letters in hexadecimal. Now for octal to binary, you convert each octal digit to a 3-bit equivalent binary representation. Then you just write them together from left to right. The same is true with hexadecimal to binary, except that you write them in 4-bit equivalent binary representation. So 108F to the 16 is this one in binary. So you write them from left to right. Then binary to octal, you group them in bits of 3s, starting on the right and convert to octal digits. So given this 10110